Okay, hi. We're going to talk about stuff from lecture 18 today. This is on sampling distributions and the central limit theorem. You'll find out what that means in a minute. Remember that watching videos is no substitute for reading the book and notes. Alright, I have to just talk for a second. Suppose we were asked to estimate the mean of a population. Of course, what we would do is we'd go out and take a sample, the best sample we could afford, and then we would find that sample mean, and we would say that sample mean is our estimate for the population mean. So let's say that sample mean is called x bar, and that is our estimate for the population mean mu. All right, we're done with that. And then the next day, somebody comes along and says, well, I need an estimate for that same population. Unfortunately, we've thrown out all of our sample data, so we go and gather a new sample and take its mean, and let's call this one x bar, so we can call that one x bar sub 1, so we can call this one x bar sub 2. And now x bar sub 2 is our estimate for mu. Well, these two are probably not equal. So which one is better? Which one should the customer take? And suppose it happened again, x bar sub 3, and so on, right? If a bunch of these sample means is known, which one should we choose? How likely are they to be good estimates of the population mean? And is there anything we could do to improve them once we have a bunch? Like, if I had a bunch of these, the first thing I would think of is, well, I'm going to just average those, however many I have. So you have k of them, and divide by k. I'd take the average of the estimates. Right? That seems a sensible thing to do, and in fact it is a very sensible thing to do, as we will see in a moment. Okay, suppose we had a bunch of these and plotted them on a number line, which I'm going to call the x bar axis. I'm often going to think of x bar, or equivalently capital X bar, as being a random variable, the values of which are possible sample means. So maybe I would find x1 bar is there, and I would find x2 bar is there, x bar 1 and x bar 2, maybe x bar 3 is there, and x bar 4 is there, and maybe sometimes I'll get one that's pretty far away, bound to happen, and so on. If I keep doing that over and over again, right, suppose I took all the possible samples of a given size. I'm assuming all the samples are the same size here, though I didn't say so. Right. I'm assuming they were all the same size. I take the sample mean for each one of them and put it on the number line. What is it going to look like? Well, it turns out that it's going to be approximately normal. More than that, I'm going to state this as a theorem in a moment, but more than that, not only are they approximately normal, but exactly what you hope is true. The mean of this distribution, the mean of the x bar distribution, or these x bars if you like, is exactly the population mean. That can be proved. And what's more, the standard deviation of this is completely predictable. If you know the standard deviation of the population, then you can compute from it the standard deviation of the sample means. And that's most of the content of the central limit theorem. I'm going to state it in a sec, but let me get a little vocabulary. First, the mean of the sample means is denoted mu sub x bar, and the standard deviation of the sample means is sigma x bar. And this thing is also called the standard error, formerly the standard error of the mean, but since it's hardly ever used for anything else, just standard error will do. And this distribution of sample means here is actually called the sampling distribution of the sample means, a term which I will avoid whenever possible. All right, so let me just go ahead and state the central limit theorem, and this is written out in some more detail in the book and notes. But here we go. This is the central limit theorem, and this thing's a big deal. You may remember that I said back when I was talking about the law of large numbers that there were really two theorems that kind of underpinned all of statistics. The law of large numbers is one of them, and this thing is the other one. And it says something like this. Suppose that samples of size n, so they're all the same size, are repeatedly drawn from a population with mean mu and standard deviation sigma. Then, if n is greater than or equal to 30, or the population is approximately normally distributed, then first of all, the sample means are approximately normally distributed. And what's more, the approximation gets better as n increases. So if you use larger sample size, you get sample means closer and closer to being really normally distributed. And second, mu x bar, the mean of the sample means, is equal to the population mean, and sigma x bar, the standard deviation of the sample means, is equal to sigma over the square root of n. To get sigma x bar, which is the standard deviation of the sample means, or the standard error if you like, you just take the standard deviation of the population and divide by the square root of the sample size. All right. One observation here, this theorem does not say anything about the distribution of the population. And in fact, it doesn't matter what the distribution of the population is. If you have large enough samples, then the sample means are going to be normally distributed regardless of the distribution of the population. If the population is really bizarrely distributed, it is true that sometimes you need more than 30 as a sample size in order to get some decent approximation to normality for the x bar. But for most things that you work with, 30 is fine, and we're just going to use 30 as a cutoff size. All right. Very often, this thing is just abbreviated to CLT, and I'll do that just like everybody else. All right, let me do some examples here. So, I'm going to turn this page over. So suppose that a random sample of size 30 is taken from a bimodal population with mean 8.3 centimeters and standard deviation 1 centimeter. What is the probability that the mean of the sample is within 0.3 centimeters of the population? And here's a picture. It may be difficult to see, but I've drawn a bimodal population distribution. And because we have a sample size of at least 30, it's exactly 30 in this case, we can conclude that the sample means are going to be approximately normally distributed. Of course, I have them exactly normally distributed here, but that's fine. We should just think of them as being that anyway. All right, what is the probability that the mean of the sample is within 0.3 centimeters of the population mean? So we're being asked for the probability that x bar is within 0.3 centimeters of the population mean, which we were told is 8.3. That is, we want the probability that x bar, let's see, 8.3, if you go 0.3 to the left, you get to 8. If you go 0.3 to the right, you get to 8.6. Right? Here's the mean, 8.3. Go 0.3 to the left, you get here. 0.3 to the right, you get there. So this is the same as the probability that x bar is between, well, is between 8 and 8.6. All right. Now that's the sort of thing I can compute with normal CDF. Right? This is going to be normal CDF of 8 to 8.6. There are the endpoints of the interval I'm interested in. The mean here is going to be 8.3. And now what's the standard deviation? We're talking about the x bar curve here. We're finding a probability for x bar. So the standard deviation is going to be the standard deviation of the population divided by the square root of the sample size. A really common source of error in this sort of problem is to use the population standard deviation when you're finding probabilities about the sample means. To use the standard deviation for x when you're finding probabilities about x bar. And now, of course, you don't even need to see me do this, because you can easily do it yourself. It's about 0.8648. Okay, let's do another. All right, John computed the standard error for a certain population using samples of size 30. Jane did the same, but using samples of size 40. Which person got the larger number? So let's see. For John, we have n equal 30, and for Jane, we have n equal 40. So John's estimate of the standard error would have been sigma x bar, would have been the population standard deviation divided by the square root of 30. Jane's estimate would have been the population standard deviation divided by the square root of 40. Now 40 is a bigger number than 30, so the square root of 40 is a bigger number than the square root of 30. And so when Jane does her estimate, she's dividing by a larger number than John is, so she's going to get a smaller result. So John's is bigger. John's result is the larger one. Okay. He's dividing by a smaller number, so he's going to get a larger result. Okay. In general, will sigma x bar be larger than sigma, smaller than it, or equal to it? Well, let's see. In general, sigma x bar is sigma over the square root of n. Now, how can these two things be equal? Oh, sorry, that's not the question. The question is, how could sigma over the square root of n be equal to sigma? Well, only when n is 1, right? The only way that can happen is if the square root of n is 1, so we're dividing by 1, and that can only happen if n is 1. And so, anytime n is larger than 1, you're going to be dividing sigma by something larger than 1, which means you're going to get a result smaller than sigma. And so, in general, for n greater than 1, sigma x bar is going to be less than sigma. The standard deviation of the sample means is smaller than the standard deviation of the population. The standard error is smaller than the standard deviation of the population. Okay. I want to write this out because it's a question you're going to have to answer for yourself many times in the remainder of this course. The question is, when can you use the CLT? And what that really means, and I won't write it here, is when can you apply the central limit theorem to guarantee that the distribution of sample means will be approximately normal? That's what I mean by when can you use the CLT? Well, the answer is when n is greater than or equal to 30, or the population is approximately normally distributed. see, there are going to be lots and lots of problems and techniques coming up, confidence intervals and hypothesis testing stuff. And you can't do any of that stuff without being able to apply the CLT. That is, without having a sample size of at least 30 or the population approximately normally distributed. It's fine if you have both, of course. And in general, you're just going to be asked the question. And sometimes the answer to the question is going to be, I can't do this test, or I can't construct this confidence interval because I can't use the CLT. You just have to make yourself aware. Every single one of those problems should be started with the question, can I use the CLT? You know, we're not trying to trick you or torture you by sticking in these problems where you have to be aware. We're trying to train you. I mean, it's very important to use statistics correctly and to know when you can and when you can't do something. I guarantee you that just yesterday, a minimum of 100,000 mistakes were made with statistics by people just not paying attention to the circumstances under which they were using whatever part of statistics they were using. It's extremely important. All right, let's do another problem here. If x is normally distributed with mean 14.7 and standard deviation 1.6, what is the probability that the mean of a randomly chosen sample of size 32 is greater than 15.2? So we're looking for the probability that the mean of a randomly chosen sample of size 32 is greater than 15.2. That is, we're being asked whether x bar is greater than 15.2. So the first question we ask is, can we apply the CLT here? And the answer is yes. Right? First of all, we have a sample size that is large enough. Right? So any sample of a size at least 30, we can apply the CLT. So we're good there. Actually, we were also told that the population is normally distributed, so we could have applied it even if the sample size were less than 30 here, but okay. Well then, this is pretty easy, right? What is the mean for the x bar variable? The mean is just the mean of the population, which is 14.7. And what's the standard deviation of x bar? Well, it's the population standard deviation over the square root of the sample size. That is, it's 1.6 over the square root of 32. So when I go to normal CDF, right, the probability that x bar is greater than 15.2 is going to be normal CDF of 15.2, comma, infinity, or the TI's version of infinity. And then the mean, 14.7. And then the standard deviation, 1.6 over the square root of 32. And that works out to be 0.0385, approximately. All right, here's another one. For residents of Snowbird, the average phone bill is $64. Bill amounts are normally distributed, and the standard deviation is $9. First, what's the probability that a randomly chosen bill is less than $58? So let's let X be the bill amount in dollars. The bill amount. Well then, there's no sampling going on here. If you like, the samples have size 1, and you get the same sort of thing. But we'll just say there's no sampling going on here. So we're being asked for the probability that X is less than 58. And there's absolutely nothing. Oh, hold on. Can I use the CLT? Oh, you don't have to think about the CLT, right? Because there's no sample mean going on here. We're looking for probabilities about X and not X bar. Okay. What's the probability X is less than 58? Well, that's just a normal CDF, and you can do that without any further help from me. It's about a little more than 1/4. All right, what's the probability that the mean of a randomly chosen sample of 36 phone bills is less than $58? So now we're being asked for the probability that x bar is less than 36? Well, so first question here is, I do have an x bar involved. I'm looking for a probability about sample means. I do need to know that I can use the CLT, but of course I can. Right? First of all, my sample size is 36. And second, if you look back at the problem, it said that bill amounts are normally distributed. So this population of bills here is normally distributed, so I can use the CLT for that reason also. In this case, I'm going to be looking at the x bar variable. So the mean of the x bars is the same as the mean of the population, which is 64. And the standard deviation of the x bars is the standard deviation of the population divided by the square root of the sample size. That is, it's 9 over the square root of 36, which happens to be exactly 1.5. So you can figure this out. It'd just be normal CDF of minus infinity to 58 with mean 64 and standard deviation 1.5, and that would work out to be about 0.00003. That's a tiny probability for a sample of size 36 as compared to 1/4 for just a randomly chosen phone bill. And here's what's going on. The bill amounts here are normally distributed with mean 64 and standard deviation 9. Then I've drawn this curve right here for that, the PDF of that normal distribution. But the sample means they have the same mean, but they have a much smaller standard deviation. So if you look at x equal 58 here, the bill amount of 58, the probability underneath the population curve here of finding a bill amount that's less than 58 is pretty large. It's about 1/4. Right? So about 1/4 of the area is under this broad curve here is to the left of 58. But only a very tiny fraction of the area under the sample means curve is to the left of 58. Okay? You can think of that as just a sample mean, a sample of size 36 gives you way more information than just knowing, just knowing the distribution of the population. All right, 2 more examples here. A certain quantity is normally distributed with mean 42 and standard deviation 12. You take a sample of size 9. What is the probability that the mean of your sample is between 38 and 46? So we're being asked for the probability that x bar is between 38 and 46. Okay, so we must ask whether we can use the CLT. Well, our sample size is quite small. It's 9. So that won't let us use the CLT. However, we are told that the population here, the certain quantity, whatever it is normally distributed. And so, yes, we can use the CLT. And after that, it's just like the rest of the ones we've been doing. Right? This would be normal CDF of 38 to 46 with mean 42 and standard deviation 12 over the square root of 9. Right? And I trust you could put that in your calculator and find the number. All right, the last problem. This problem is conceptually more complicated than the earlier ones, but it contains an idea that's going to be really important to us in the coming weeks or over the coming lectures. Okay, to meet a customer's requirements, the diameters of the ball bearings made by a certain machine must be normally distributed with an average of 2 millimeters and a standard deviation of no more than 0.1 millimeter. An inspector measures 35 bearings and finds a mean diameter of 1.95 millimeters. Should he consider the machine to be operating within spec? So let me just go over here and draw a little normal curve. We'll say that this has mean 2 and standard deviation 0.1, so this would be 2.1, 1.9, and so on. 1.95 under this graph looks pretty close to 2, right? I mean, it looks like there's a great probability that if you chose a ball bearing at random, it would have a diameter less than 1.95, even if the machine were working correctly. Right? Knowing that this normal curve is the true distribution of the diameters means the machine is working correctly. So even if the machine is working correctly, choosing a ball bearing at random, there'd be a large probability that that ball bearing would have diameter less than 1.95. What about for a sample of size 35? Well, as you've seen in an earlier problem, right, the standard deviation of a sample that size is going to be much, much smaller. Right? It's going to look kind of like this. It's going to be very tall and narrow. Right? Of course, my drawing is terrible, but that's the idea. So there's going to be a lot less area to the left of 1.95 under that sample means curve. We'll call this one x and this one x bar as usual. Excuse me. Well, let's find out what that is. So what we're going to do is we're going to assume that the machine is operating correctly. We're going to assume the machine is operating correctly. Okay. Then the population, if x is the diameter of a ball bearing, then the machine operating correctly means that x is approximately normally distributed with mean 2 and standard deviation 0.1. Okay. In that case, x bar is approximately normally distributed with the same mean, but with standard deviation 0.1 over the square root of 35. That's about let's see, 0.0169 approximately. As you can see, right, and as you would already have realized from the previous example, that's a much smaller standard deviation. The curve is very narrow, and there won't be much area to the left of 1.95. So the probability that x bar is less than 1.95, less than or equal to, right? Why did I pick less than or equal to? Because the inspector has actually found a sample mean of 1.95 millimeters. Right? I want to know the probability of, if the machine is working correctly, what's the probability of finding a sample mean for a sample that size that is 1.95 or less. Right? That will tell me kind of an idea, that will give me an idea of just how likely it is to find a sample mean that bad. Well, it is bad because it's not right at 2. What's the probability of finding a sample mean that bad or worse? Okay. And again, I just punch this into normal CDF, and I can find out that that's about 0.0015. Well, that's pretty small. Right? That's 15 out of 10,000. So if you took 10,000 of these samples, right, size 35 at random, you should see this no more than 15 times. No more than 15 times would you see a sample mean that was down here at 1.95 or lower. That's pretty rare, and so you would probably, the inspector would probably conclude from this that the machine is not operating within specs, or at least seriously needed to be checked. All right, that's about all I've got to say for this section.